Karol Szczypkowski from Wrocław University of Science and Technology, who will talk about non-symmetric Lévy-type operators. Karol, please.
Thank you. So obviously, many thanks to organizers for doing this, for organizing such an event, and for giving me a chance to give a talk. So yes, the title is Non-symmetric Lévy-type operators. I'm not sure if it fits very well to the topic of this course and this week of meetings, but there will be Fourier transform at some point, so at least that. So this talk will be based mainly on the first paper that I show you here, which is a preprint with my PhD student about non-symmetric Lévy-type operators. But I will sometimes refer also to other papers. The last one was published in 2019 in Journal of Differential Equations. The second one is still a preprint under review, but mainly I will focus on the results that we obtained with the PhD student. And because usually I'm pretty afraid that I will not have enough time to present results if I leave them at the end. So the plan for this talk is that first I will present results, but without specifying assumptions. And you can see that I put them at the very end, and in between I will give some motivation, introduction, like explain the topic, like you could see non-symmetry, and there is some method that we use to solve the problem that I will state in the introduction. Okay, so that's the plan, and we will start with the main result. And here, well, I have to tell you at least something. We will try to solve this kind of parabolic equation, and the operator on the right hand side is of the following form. So it has this local part, first order term. We calculate the gradient of f, and here we have this integral, which is non-local part of this operator. The value of this integral depends on the value of x, not only around point x, but everywhere. So if you change the function somewhere far from x, it will affect this integral. And we have two main objects here, the coefficient b here, and very important for us, coefficient kappa. I will briefly say what we want to assume. We will assume that this function j will be comparable with some profile function mu. We'll also assume that b is bounded and Hölder continuous. And we'll assume the same about the coefficient kappa here, but with respect to the first coordinate. So it's going to be bounded kappa, but it's going to be bounded above, but also bounded. It's going to be positive, so away from 0, and Hölder continues in this way. So x minus y to some power, say epsilon kappa, with epsilon kappa in 0, 1. Okay, Karol, there will be, yes?
Sorry for interrupting. What is new?
New, it's going to be some profile function. I will specify later in the assumption section of my talk, okay? So this function, okay, maybe this function will be comparable with some function that depends only on the radius, on the absolute value of z, okay? And it should be such that it integrates, this function should be integrable with z square around 0 and with 1 at infinity, but this will come later. And this will be our assumption. There will be more, but I don't want to go into that details. And now I would like to present the main result. So to formulate the theorem, I will use the notion of a kernel on time space. So we will have S and X fixed point in time and space. And we will discuss this mapping, this kernel. It's going to be, could be signed, but finite Borel measure whenever we are in a bounded interval in time. Well, and you can be on full space. So then we want this to be a Borel measure. And the first result is under assumptions A and A star, which I will specify at the very end. We fix point in time and space, and suppose that we have two kernels on this time space as defined above, such that they provide a minus inverse operator to that object. Phi here is a test function. And what we say is that if we have two such kernels, then they actually have to be the same. So this addresses a uniqueness question for our equation, because this is a weak formulation for that equation. Okay, whenever you have some questions, please ask. So that's the first result. And the second result addresses the question of, yes?
Sorry, Karol, so it's basically, this is the uniqueness result for the joint operator, right? For L.
No, this is for the operator actually. Because you see, the thing is that if you want to solve your equation in, actually I should write maybe in, it's not for the adjoint operator, it's for the operator really. Because it's actually in variables u. I should have written it like this, in variables u and in x, okay? Mm-hmm. So here you get 1 minus from sort of integrating in time here by integrating by parts. But then when you throw this operator, you put a conjugate operator into z, but then you have to throw it again into x, and you are back to the original operator. Mm-hmm. So it's for the operator.
Oh, yeah. Thanks.
In the paper number 2 and 3, we were actually proving something pointwise, and well, we used the same approach and similar approach, maybe, let's say. And okay, and there is we have some result which shows that it's the next theorem. I will show you an existence result, and the kernel we obtain, it almost satisfies the equation that we want to solve. So that one, there is some problem with applying this operator to the object that we have. But okay, so the next theorem says that under the same assumptions, we actually have such kernel that is given as an which has integral kernel. So there is, here you could actually put this function p. So there is such kernel, but actually it's absolutely continuous with respect to Lévy measure. Now, because we actually construct this function, we take the function that we constructed. There are some details here. We have this function defined. If you just use the uniqueness result, you have it defined for almost every time variable, but the one we constructed, it's well constructed for every t. And now we take this function and we define this object, which we show under the same assumptions that it's actually a strongly continuous positive contraction semigroup on C0 with supremum norm. C0 is a space of continuous functions vanishing at infinity. Now we also say something about the generator of this semigroup. So, and about this semigroup a little bit more. So it's a probabilistic semigroup, or this function is probabilistic, so it integrates one-to-one. You can also apply this operator to functions from larger class, like Borel bounded functions, and then it immediately transfers those functions to continuous bounded functions. In processes, is known as this property is known as strong Feller property. And we also have that twice differentiable functions in zero, they are in the domain of this generator, and it actually agrees with our operator on those functions. And more, actually, this generator is the closure of the operator that we started with on smooth, compactly supported functions. And we can also show that this semigroup is differentiable. Okay, and we actually calculate, we give some formulas for the generator applied to this semigroup, or you can say that just the derivative, well, this is equal to the derivative in time of the semigroup. And under some stronger assumptions, we also give estimates to this function ptxy.
Karol, sorry for interrupting once again. I hope you don't mind. What do you mean differentiable semigroup?
Differentiable, so in the supremum norm, so because we are, so this limit, let's say f pts t minus s, this exists in the supremum norm.
Mm-hmm.
So it converges to some element. Actually, it converges to something that we call if s goes to 0, if t goes to s.
But it's strongly continuous, right? So
it's strongly, but this is for s positive, right?
Mm-hmm.
So this in supremum norm, this goes to 0 as t goes to s. So this is differentiability of a semigroup on the Banach space that we have in this Banach space. Yes, you have strong continuity, but that's something else. Oh, and this holds, well, it holds for every function f from the Banach space, right? Not only for functions which are in the domain.
Oh, okay, no, okay.
That was your question.
Mm-hmm.
Okay, so these are the results. Now I will try to explain why we are dealing with those operators and why non-symmetry kind of appears in the title. So the general aim is that we have some linear operator and we want to find the structure behind this operator. And in different theories, you either try to find a fundamental solution to this equation, or you try to find a semigroup associated or generated with this by this operator. And if you're lucky, you have kernel, integral kernel of this semigroup. And some people try to associate stochastic process with this generator, and such that it generates in some sense, it's generated in some sense by this operator. And you want to sometimes find the distribution of this process, so to find this function pt. So there are those probably more, but at least these three reasons why you want to, what kind of structure you want to associate with the linear operator. And methods could be like for PDEs, it could be the parametrics method, which we will actually use in some way. For semigroup theory, you could use Hide-Yoshida theorem to try to associate a process, a semigroup. And what does it mean to associate a process with a generator? Some people try to solve martingale problem. So they try to make this expression. So here is the operator. They try to find a process that will make this expression to be a martingale. And in the second and the third question paper that I mentioned, we were actually doing all three. Now let's maybe focus more on this analytic part. Okay, so why? What kind of operators we are interested in? And so if you start from a semigroup on the same space that we had in the theorem, and if you, this is the definition of the generator. So whenever this limit exists in this Banach space, then f is in the domain of L, and this limit is equal to the generator applied to this function. And there is a very well-known Waldenfels theorem, which says that if the semigroup is regular enough, it's a strongly continuous positive contraction semigroup. And if you have that smooth functions are in the domain of this generator, then necessarily on those functions, it has this specific form. So the generator is equal to this explicit operator. And we have several parts here. This is zero order term, first order term, second order term, and this is the integral non-local part. And the very important feature here is that this measure that appears here, it should integrate z square at 0 and 1 at infinity. This measure has this property. So we know that we have, if we have a nice semigroup, then we have explicit, and with which domain we have explicit operator, but the converse result in general, it does not exist. So there is always a question, give me an operator and let's try to find a semigroup associated with it. So people take different classes of such operators and try to prove that there is actually a structure behind it. Okay, and yes? Okay. So there is one case when the situation is simpler, and these are convolution semigroups. If your semigroup is of this form, it's not exactly convolution, but almost convolution, but the measure that appears here forms a semigroup with respect to convolution. So you convolute these two measures at t and s, and you get the measure at t plus s. If you have this kind of measures, which are vaguely continuous, you don't have to be familiar with that, but we want them to be probability measures, then it is known that, like, we calculate the generator, and then what we know is that actually C02 functions are in the domain, and for those functions, the generator as above, but here for this better class, larger class of functions, we have explicit formula. So again, we have this first order term, second order term, and the non-local part. Well, we don't have C times F here, but you can add this simply by multiplying the semigroup by e to power CT. So that's why it does not appear, and we want to make some relation to processes, so we don't want to add that, because that would mean that it's not really probabilistic process. So okay, so here we don't have this C, but we can easily add that to the picture. And here we also know that those smooth functions, this is the core of the operator. So it means that if you close that explicit operator on these functions, then you will get your generator with its domain. And here, the measure that appears here again, it satisfies this integrability condition. And here, B, A, and the measure, they do not depend on X, so they are constant in this sense. Moreover, A should be a non-symmetric, non-negative definite matrix, B is just a vector in RD, and the measure N should satisfy that. And then you have one-to-one relation between such class of measures as here, vaguely continuous probability measures, and Lévy process. So here, everything is clear. Now what people try to do, they try to start with some operator that is similar to that, but and transfer the knowledge from this situation with constant coefficients to the case with non-constant coefficients. Okay, and this situation has another good structure, because we can calculate Fourier transform because everything is convolutional. So if you calculate the Fourier transform of this measure pi t, or you calculate the Fourier transform of the distribution, exactly the distribution of this process, you get this exponential term, and this function psi, it also has this constant coefficient b, matrix A, and the measure. And well, this is a well-known result that if a Fourier transform is in L1, you can invert this Fourier transform and you obtain the density of the Lévy process, which is also then these measures that are here, they are absolutely continuous, and this is the density. And just to let us look at the absolute value of that. Clearly, well, we know that this is e to minus the real part t is real, so this is just the real part of this function here. This is called the characteristic exponent, and it has this form. It just follows from this explicit formula here. Later on, we will not. We will put a to be 0 because we are mainly interested in this non-local part, okay? Good. And there is more. If this real part grows fast enough, then the function that we obtained on the previous slide, if you shift it a little bit, so if you consider function of 3 variables, time, but also x and y, and here we just put a difference between x and y, then this solves the equation that we want to solve in general, but in this particular case, so it solves the heat equation with this operator. This is the generator of the Lévy process, and we had it given here explicitly. And you can use this formula actually here in this formula, because the function here is actually smooth in x, and you can just apply the operator. So here, obviously, the semigroup that we had above, it can be written by means of this function now. So we have 3 things. We have the solution, we have the semigroup, and we have the process. So that's something that we would like to also get from Lévy-type operators. So for those operators when the coefficients are not necessarily constant. Okay, so now I will explain things. Why do we say something about non-symmetry? So in this Lévy case, so we are still in the Lévy case when this semigroup is a semigroup where we almost convolute with this measure pi t. You can actually consider this semigroup on L2, and then these operators are self-adjoint if and only if the process is symmetric. It's if and only if the generator is self-adjoint, and in terms of the characteristics that we had, like B, A, and measure N, this holds exactly when you have no first order term and the measure in the integral is symmetric. Okay, so now what happens when we try to go from constant coefficients to non-constant coefficients? So if you start with this operator, second order operator, recall that this matrix is symmetric. And well, this fits into this fact. So we have a symmetric operator, self-adjoint operator. And now if you extend it to, operators with non-constant of coefficients, you can do it in two different ways. So if you put it in a divergence form, then you get symmetric operator, and you can treat this in L2 spaces, and I'll mention a bit more in a moment. But if your structure is different, despite the fact that you still have symmetric matrix here and maybe here, this is not a symmetric operator. And so this also translates in some sense to this integral part. So if you would like to obtain symmetric operator, you would maybe take some symmetric kernel and write your non-local part in this form. And here, the theory of Dirichlet forms is applied by many people, and on very general metric spaces or manifolds. And when people talk about symmetric operators versus symmetric processes, they usually mean processes that are generated by this kind of objects. Now, in our case, because of the structure, we already start with something non-symmetric. Even if for given x, your measure here will be symmetric, still the structure of this operator is such that you cannot really put everything into L2 theory or Dirichlet forms. And these are the operators that we are interested in. They come from Courage theorems, and they kind of by definition are non-symmetric, because also we start from completely different space, which was C0. Well, we will also like to have this measure to be non-symmetric. The internal structure will be of our interest, and we will try to handle non-symmetry also in Z. Okay, but here I recall the property of this measure. It should integrate Z around 0 and 1 at infinity. Now let's for a moment assume that we have symmetry in Z. So then this non-local operator, here we have symmetry in Z. So that was the non-local operator of our interest. And because this part here, it's non-symmetric in Z, we can actually remove that. Maybe, and we can write it equivalently in this form, well, to assure that this integral is for good functions f like C2. This is fine. This is a convergent integral because of this condition. But here we would maybe have to put principal value. So people sometimes write it then in this form, but a very convenient form of this operators is the third one here, because you can take two such expressions and make substitution. You put instead of Z minus Z, but the measure does not change, you add those expressions back and you get this form. So in the symmetric case, it's very convenient to discuss this operator. Then we don't have the first order term under the integral. The only term that appears here from function f is the second term. So if you think of Taylor formula, for instance. Okay, and this in the third paper, my paper with Tomasz Grzywny, we were discussing all three of them. The last one in the symmetric case, this one in some specific case, but non-symmetric case in Z as well. And we were also discussing this operator with Tomasz Grzywny. But what I will present now and in my paper with Jakub Minecki, well, we treat more operators, and we looked into the structure of those operators a bit more carefully. Okay, so what to do if you don't have this symmetry in Z here? What you do, well, you do a very simple thing. You add and subtract this indicator function here. So the same expression, but this term is sometimes called compensation term. So we compensate instead of the level 1 at some chosen level R, and then, well, you just add and subtract, and what you are left with is this first order term. And this is called, we call this internal drift. And we will have to deal with it somehow. And most of the time, the level at which we compensate, the level R, will depend sometimes on time. But okay, so we will have to deal with this internal drift somehow. Okay, this is where the non-symmetry comes. And now the method we use is parametrics method. This is a method from PDEs. Let me try to explain a little bit. So we want to find a function that solves, that is harmonic, say, with respect to this parabolic operator. And let's say that we have this function, but we don't know the exact structure, and we kind of guess the structure of this function by taking some zero order approximation of this function and some remaining term. Okay, so because we know that this function satisfies, this is heuristic. So since we know that this function satisfies this equation, we apply this operator. So we have 0. This object we actually know because we chose our zero order approximation. So we know this term. What is unknown is this. And so we will leave this as it is, but we will shift that to other side of the equality, and actually we will call this is called minus Q0. And so Q0 is minus P0. And if we do so and we shift to the other side, we just have equation for the remaining term or remainder. We know Q0, it's here with minus. Okay, so this equation, we know how to solve because it's again, we have the fundamental solution sort of, we have the harmonic function with respect to this operator. So we can use this function to give a formula for R, and R is given by this integral. So here is this function, this solution, and here is the right-hand side of the equation. Okay. And so if we now go back to our that equation, we can write P as our zero order approximation and this integral. And now this is of such form P0 plus P, and I will, for the integral, I will use this weird notion of some kind of convolution of P with Q0. We chose P0 and we also know Q0. So these two functions are known, we don't know P. And then if we have this relation, it can be iterated. So we can replace this P here again by the same object, the same formula. So we have P0 plus, and here we put P0 plus P convoluted with Q0 convoluted with Q0. And so what one gets is P0 plus P0 with Q0 plus P convoluted, and here we have two, so I will write it, we have Q0, but here it's convoluted twice with itself here. And you can continue and you will get a series representation. So let's say P0 convoluted with, and I should sum perhaps from 0, Q0, and okay, maybe I shouldn't write this first one in this sum, but okay, this is just heuristics. So we have series expansion or series representation of our problem, and we will use this kind of approach to construct P. So we will choose good zero order approximation, we will calculate Q, and we will sum QNs. But to do so for functions, it's quite involved, and you have to make a lot of calculations. In the paper with Tomasz Grzywny and the paper by myself, it was done exactly like that, and it requires a lot of calculations and convoluting these functions with itself. And here I would like to present some very convenient analytic approach to this problem. So let's say now we will associate some operator with zero order approximation and some operator with this function Q0. So let's say that we have two operators that act from Borel bounded functions into Borel bounded functions. And as you kind of saw, I try to explain it here, this formula at the end, it can also be written now in this operator form. So our solution should be of the form, this is the zero order approximation acting on some function f, and well, okay, this is the rest is the series here. So it's again, maybe I should write it here. So you can write it P0 plus P0 convoluted with the maybe now sum from 1. Okay. If you look at this in this form, you have exactly the same here. So this is the series, but okay, the first function is convoluted with its well, the power is 1. Okay, to make it really formal, it's made in this form. I think I have some maybe notation issues here, but this is how we suppose the solution should look like. And so here is the series. We will assume several things for our, so we put some assumptions or some hypotheses on our operators P0 and Q0 to make everything very mathematically strict. So here we will use the notion of Bochner integral when we integrate these objects. So we assume in a sense that the zero order approximation is a bounded operator, and this should be uniform in T. That they should be continuous for positive T in the supremum norm. Everything is happening in the supremum norm, and this operator Q that corresponds to the kernel Q that appeared on the previous slide, it should also be bounded, but it is not uniformly bounded in T. It might explode, and here is some function RT. Let's just think that RT is T, okay? So here we actually get T to power -1 plus epsilon 0, and this is unbounded as T goes to 0, but it's integrable, and we want that. And in general, this can be a little bit more general function, and it will be useful for us to use this more general function, but for the presentation, it's good enough. Okay, and we also assume that those operators are also continuous. Okay, and so if we have that, we can sum all the series, and we can define the operator PT, our solution in a sense, as in the formula 1 here. Here. So everything is well defined, and this is an operator from Borel bounded functions to Borel bounded function. It's actually bounded uniformly in T. Everything is happening for T in 0, 1, and it's also continuous. So we have object that we can work on. Like verifying those hypotheses is not trivial. Well, you choose your zero order approximation, and then you calculate Q, and you have to you have to do some work. It's usually requires some work. Okay, we want to have a little bit more structure. We want to know a little bit more about our operators, because everything in the end will happen on the space C0. So we want this operators also to act from C0 to C0. And then obviously it's a similar result as above. Then PT that we construct, it also acts from C0 to C0. Okay, and now if we also add that our zero order approximation is such that it converges to Dirac delta when t goes to 0 in the supremum norm, if we have this, then it immediately also translates to the operator P that we constructed. So this PT here that we construct is actually the semigroup that we want to have. And that's exactly the semigroup from the theorem I mentioned at the very beginning. Okay, actually this hypothesis H0, to prove this, it's also not so trivial in applications. But here in the paper with Jakubinecki, we formulated in this form because then you just have to verify all those hypotheses because those steps were kind of known. It's not a mystery. Okay. Now, as we have our operator, we want to check more. So we want it to be non-negative. We want it to be sub-Markovian. It means that function f is smaller than 1, then PT on f is also smaller than 1. We want to have a semigroup property, and we want to find the relation between the operator PT and our operator L. This is a typical relation between a semigroup and its generator, at least for some good functions. And we also, in the paper with Jakubinecki, we also propose a general approach how to verify those assumptions. And if you check the literature, how does people prove this kind of properties? Most of the time you check that the function PTF, that this function is actually a harmonic with respect to this parabolic operator. And you use maximum principle of this operator to show that these properties hold. The problem here is that we don't know much regularity. Sometimes we may not know much regularity about the function, the object PT that we constructed. And now, maybe I will actually skip that slide. But okay, we want to associate our object PT with some operator that is decent so that it satisfies maximum principle. I don't have much time to go into details here. And because we don't have much smoothness of the object we constructed, this is an idea developed by Alexei Kulik in many of his papers to avoid the problem of not having enough smoothness of PT, which was almost like the same formula here, but with epsilon 0. So there was no epsilon here, no epsilon here. The problem appears here when whatever good zero order approximation you choose, when you try, for instance, to calculate the gradient, here there is some explosion, and very often you don't know how to integrate that. So to avoid that, he proposed to use this approximate object. And I will only show you one hypothesis that we assume, like in general, to prove the conjecture. So all the properties here. So if you assume that if you apply your parabolic operator to this object, you get some formula. Don't look at this. Just this is some formula. To prove this formula, usually you need relation between P0 and Q0, as in parametrics method in the heuristics that I showed you. But this function is smooth enough, and usually you can apply this operator and you get this formula after some calculations And then the right-hand side, it's not so hard to show that the right-hand side, as epsilon goes to 0, it goes to 0 in the supremum norm and uniformly in T if T is away from 0. So this means that this goes to 0 as epsilon goes to 0, and it means that this is actually some kind of approximate solution. And you use this solution to prove all the hypotheses. And I will skip this slides because it only says that if you have your operator is nice and you check the hypothesis, then you actually have the conjecture. So you have semigroup property, you have non-negativity, and so on. And finally, I'd like to say a few words about what are our assumptions really. So back to our operator, because we use this parametrics method to prove theorem that I showed at the beginning. So our operator was of this form. So we take some, Damir asked what was new. New was just a non-increasing function such that it integrates with z square at 0 and with 1 at infinity. It means that this is a Lévy measure. Now, what do we assume about this function j of z? We want this j of z to be comparable with this profile function. Coefficients should be bounded from away from 0 and from above as well. It should be Hilder continuous, the coefficient here. And now here I recall the real part of the characteristic exponent associated with this Lévy measure. It was of that form. And we don't use that function, it's a little bit involved. Instead of that, we use a similar function which is the minimum of 1, so it's also bounded like this function. And here it reflects the behavior of this function when x and z are small, then if this inner product is small, then this behaves like this. This object here, x is equal to 1 over r. And this is a general theory. We know that this function is, if we take 1 over r, this is comparable, not exactly with this real part, but with some majorant of this function of this real part. I don't want to go into details here. We will use this function. And what we will assume is the following scaling. We call it weak lower scaling condition. It will say something about our operator because our operator is very much associated with this profile function. And what does it say? Well, let's just try to divide by this expression, and I will put this lambda minus alpha h here. This is function h at some point r, and let's take lambda, let's go with lambda to 0. It means that this function, as lambda goes to 0, it has to increase at least as like lambda to minus alpha h. And we interpret this as in the following sense that the operator that we are dealing with is at least of order alpha h, okay? And this will be our assumption. And we also have to assume something on this internal drift. Well, we also have this external drift, but also the internal drift. And here are the assumptions. So it will be kind of bounded, but the boundedness is in the scale somehow. It depends on where do we cut. And we use this function h called known also as concentration function, and we multiply by r to sigma. So this will be assumed, and we also assume some Hilder continuity of this internal effective. This could be called effective drift, and this is also Hilder continuous, but again it depends on where we cut. Okay, the same condition with star is only that we strengthen a little bit. We put minimum with 1 here. Okay, this is locally in x and y, and here global, and we put minimum with 1 here. And then here I will not really say much, but we have to assume something about these coefficients sigma, epsilon j, sj that appear here. And we consider the case if we have 6, then we have the assumption A. If we have 6 star, we have the condition A star. And under those conditions, our main results were stated. Maybe one very interesting case when all these assumptions are satisfied is when sigma is 1, then this is trivially satisfied because alpha h is positive. And also this one is satisfied when sj's are 1 because this is positive. So when you can put 1 here and 1 here, then you have your assumption satisfied. And actually in the paper with Tomasz Grzywny, that was the case, but we did not really recognize those conditions. It was just involved in calculations somewhere. And I don't have time anymore. I will only show you one example, and I will stop after this example. Because there is one operator, which is surprisingly, because the literature on the topic is extensive, it's extremely huge. But then it turned out that the very simple example has not yet been covered. So let's even take dimension 1. Okay, don't look at this phi because I didn't have time to introduce that. And let's consider this operator. So here we have 1 plus 1, because this one comes from the dimension, this comes from alpha, or you can say alpha h, which is here. And we will take very specific coefficient, which is a product coefficient. It's given here explicitly. And it turns out that this was not covered in the literature. And the problem was that if you now try to verify our assumptions C5 and C6 star, this internal drift is Hölder continuous, but there is this logarithmic explosion as r goes to 0. And this is because this is exactly equal to that. And this is one of the reasons why, if you look at assumptions in many papers, they do not allow any explosions here. It has to be, this internal drift has to be just uniformly in R Hölder continuous. And so this was not covered. So we covered this operator, but also here I have many more. And I will just skip all these things, and I will thank you for your attention.
Thank you very much, Karol, for wonderful talk. Let's thank Karol. And questions, comments, suggestions?
I have a question. So, Karol, can you comment in general on this non-local parametric method? So you require Hölder continuity of kappa. But what about this external drift, the B term? What kind of regularity do you require?
Well, here it actually follows from those assumptions that it's bounded and Hölder continuous, and it's even for stable processes. Maybe the result we obtain is not the sharpest possible for this external drift. This was not the main object of our attention. Okay, we were focusing on this internal part that, for one stable, turned out to be larger than the external.
Mm-hmm. But in general, this sort of non-local parametric method, is it a restriction significant? Like,
yes, so there are there are restrictions because those operators also come from SDEs,
right?
And it is known that when you have this drift term, the external drift term, if you don't have enough regularity, then there is no weak solution. No, there's no uniqueness, I guess.
But it's
I don't know exactly which solution now, but
but it's pretty far from Hölder continuity, nevertheless.
No. You have Hölder continuous coefficient, but not enough Hölder regularity. There is something which is known as balance condition. You add the regularity of the. You have alpha stable.
You mean
Yes.
you mean take the sort of, if you consider well, sort of the principal part, if it's irregular, then your drift has to be regular enough. That's what you mean, right?
Yes, regular. So you just have fractional Laplacian of order alpha, and you have your drift of which is beta Hölder continuous. This has to be greater than 0. This is the balance condition.
Mm-hmm.
If you don't have this, if you have strictly like that, then I think for every such combination, you can construct example where you don't have uniqueness.
But so if you're saying fractional Laplacian,
yes,
plus ordinary drift, but even if you take it to be, say, bounded in L infinity.
yes, bounded and Hölder continues with this Hölder coefficient.
Right, but it can, right, and then you're saying that the counterexamples come when you're sort of
Your
have a
Hölder
negative
continuity is not large enough.
Mm-hmm. Okay.
Yeah, so you cannot just have any Hölder continuity. There are some bounds, and yeah, it's an interplay between the regularity of the operator and the regularity of the drift.
Mm-hmm. Okay, thanks.
More questions to Karol? If not, let's.
Wonder,
Oh,
okay.
yes.
I wonder
Sorry.
if you require less from the estimates from the semigroup, the resulting semigroup, can you relax the assumptions somehow?
What do I assume? Sorry.
The question is, sorry if I'm not audible. If you require less from your semigroup, there's like estimates, can you relax the assumptions somehow? Like not require pointwise bounds?
Well, we don't always prove pointwise bounds, but you mean in the construction, we start from some 0 order approximation, right? And you ask if it's possible not to start with some good bounds, right? So we start with good bounds. I think I have a slide here somewhere. So we start, because the method is, how do we choose 0 order approximation? You take your operator, you fix coefficients here and here, and then you get actually a Lévy operator. And here, everything I said about Lévy operator applies, and you have a density. And we have a lot of results about bounds for this density and its derivative. So we have good bounds, but if you start with bad bounds, it's still possible. But you cannot choose your 0 order approximation in such a kind of classical way.
Thank you.
More questions? If not, let's thank Karol again.
Okay, I shall stop sharing
Yeah.
screen.
Is Roman here?